If the concentration decrease, system will react to produce some of it. For example, when we remove PCR3. When PCR3 removed, there are more product than reactant. So in this situation, QC greater than KC and the system is not at equilibrium. The reaction quotient is written as a QC equal concentration of product divide with concentration of reactant raised with sum of its power of coefficient. In this situation, system will reduce the disturbance of decreasing of PCR3 by shift the reaction to the left and make concentration PCR3 and Cl2 increase respectively, where PCl5 will decrease in concentration. Change in pressure or volume only involve system with gaseous component. Liquid and solid are nearly incompressible. Pressure change can occur in three ways. First, changing concentration of a gaseous component. Second, adding inert gas. And third, changing the volume of the reaction vessel. Consider of this reaction: PCl3 plus Cl2 to produce PCl5. There are 2 mole gas in the reactant side and 1 mole gas in the product side. Decreasing the volume will increase the pressure. So in this state, system is not at equilibrium, QC not equal to KC. So system will reduce the disturbance by reducing number of gas molecules. So system will proceeding to the right and make concentration PCl3 and Cl2 decrease and concentration of PCl5 increase. When the pressure decrease by increasing the volume of the vessel, the gas pressure immediately decrease. So in this state, QC not equal to KC. So the system not equilibrium. So the system will reduce the disturbance by increasing number of gas of molecule, proceeding system to the left and make concentration PCl3 and Cl2 increase, where concentration PCl5 decrease. So keep in your mind, decrease volume or increase pressure, system will shift the equilibrium to the side with fewest mole of gas. Increase volume or decrease pressure, system will shift the equilibrium to side with most mole of gas. Change in temperature. Only temperature change can alter K, equilibrium constant. The reaction forward is exothermic reaction. So heat release for this reaction. For exothermic reaction, heat as a product. And endothermic reaction, heat as a reactant. Here is reaction pathway for endothermic and exothermic reaction. For endothermic reaction, the enthalpy of product greater than reactant. That give the delta H sign positive. Where exothermic reaction, the enthalpy of product lower than enthalpy of reactant and give the sign of delta H negative. For exothermic system, heat as a product. Increasing the temperature in the system will make the system will respond by decreasing the temperature of the system. Equilibrium position shift to the left to absorb heat from the system, and at equilibrium amount of reactant increase, amount of product decrease, value of equilibrium constant K decrease. Decreasing temperature in the system, system will respond by increasing the temperature of the system. Equilibrium constant position will shift to the right to release heat to the system. At equilibrium, amount of reactant decrease, amount of product increase, and the value of equilibrium constant K increase. For endothermic reaction, heat as a reactant. Heat absorbed in this reaction. Increasing temperature in the system will respond by decreasing the temperature of the system. Equilibrium position shift to the right to absorb heat from the system. And at equilibrium, amount of reactant increase, amount of product decrease. Value of equilibrium constant K decrease. Effect of catalyst. The catalyst will speed up a reaction by providing alternative mechanism with lower activation energy, increasing forward and reverse rate to the same extent, shorten the time taken to reach equilibrium. But remember, catalyst has no effect on the equilibrium position and value of Kc. This is reaction pathway or reaction progress. For both reaction, which one contain catalyst and another one has no catalyst. Or in other way, we can say one reaction with catalyst and another one without catalyst. According to the activation energy EA, the uncatalyzed or reaction without catalyst, the value of EA is greater than EA from the reaction with catalyst. By reducing the EA activation energy, we speed up the reaction to achieve equilibrium. So the one with catalyst will react more faster. So keep in your mind, changing concentration, pressure, volume and temperature will shift the equilibrium. But addition of catalyst will not change the equilibrium. Changing concentration, pressure, volume and catalyst will change equilibrium constant, value of K. But changing the temperature will not affect or change the value of K. Application of chemical equilibrium. For example, in the production of ammonia, that is one of the important components to provide or increase yield of crop. Over 80% of ammonia is used as fertilizer. When applied to the soil, it helps to increase yield of crop. Nearly 30% of nitrogen fixation on Earth is accomplished industrially through the HABER process for the formation of ammonia from its element. The process was developed by Fritz Haber, German chemist, in 1913.